Right, okay, so welcome everyone. We're very happy to have Daniel Cremers speaking this week. So Daniel is Professor of Informatics and Mathematics and Chair of Computer Vision and Artificial Intelligence at the Technical University of Munich, but he's currently on sabbatical at the University of Oxford. Daniel's background is he did his undergraduate and master's from the University of Heidelberg, and his PhD from the University of Mannheim. Did a postdoc at UCLA, which I didn't realize until I researched you. You're also a researcher at the Siemens Corporate Research in Princeton and an associate professor in Bonn before moving to Munich. You've won sort of many awards, including like the best paper in 2003 from the Pattern Recognition Society. You won the Olympus Award or the German Pattern Recognition Award in 2004. The UCLA Chancellor's Award for Postdoc Research in 2005, and the Gottfried Wilhelm Leibniz Award in 2016. So we're very happy to have you come and speak into our seminar this week. You'll be talking about self-supervised learning for 3D shape analysis. So, please.
Thank you very much, Matthew. Thank you for the introduction. It's a pleasure to be here. Thank you for organizing, to you and the whole team. This is a really great series, and I'm happy to contribute to it. The work that I'm presenting is on learning-based approaches for 3D shape analysis. And in fact, it's collaboration of a number of people, most importantly, current and former students of ours, and the main people behind this are Marvin Eisenberger, Aysim Toka, and Zora Lena. And so most of the work is really the credit goes to them. 3D shape analysis is a topic that I've always found fascinating, because we're surrounded by sorry, the slides. We're surrounded by 3D shapes. The world is a 3D world. And for me, a central part in artificial intelligence is to bestow machines with the ability to understand that world they live in, right? And understanding the 3D world means you have to relate different 3D objects. And for me, this has always been fascinating. We as humans, we have two hands typically, and we see they're similar, right? But how do you actually quantify shape similarity? How do you define, mathematically speaking, how do you represent shapes? How do you quantify distances between shapes? How do you define metrics on spaces of shapes? And it's not only defining respective meaningful metrics for shape similarity, but it's also being able to compute them efficiently. And so it's both a mathematical, but also a computational challenge, and often very fundamental, sometimes NP hard challenges that you face. For example, when you look at shape similarity, you see notions of shape correspondence, shape interpolation. Humans would say these two animals are similar, but how can you, bestow a machine with the capability to do that, to reason in that fashion? Why do I think shape analysis is increasingly important now? Is because over the last years, my team and others in the world have developed techniques like this one that allow you with just a single camera in the matter of no time to create complete 3D models of the world, of people, of objects, of rooms, of everything, right? And with that ability to capture 3D models, this is like a head, a top part scanner, and this is kind of a full body scanner that we developed to scan this. On the left side is the former president of TU Munich. On the right side is the Prime Minister Markus Söder, Prime Minister of Bavaria, who I'll be seeing tomorrow again on the Bavarian AI conference. And everyone wanted to get scanned, right? Wanted to get 3D models of themselves. It's become quite popular. It's, obviously to some extent a toy, you could say, but it shows that, we have the ability to capture the 3D world, not just the static 3D world, but we can even go further. And as you can see, these are by no way recent works, right? This is like almost 10 years ago. We were able to recover the shape of 3D objects in time, right? We can film actions like this one from synchronized cameras, and we can recover the action at a level of precision, whereas you can see the entire rope is faithfully recovered. And with that ability to tap into cameras in order to reconstruct 3D shape, the obvious next question is, how can we understand shapes? And there's been a lot of work on 3D shape analysis. What I want to focus on in this presentation, due to the focus of this seminar series, is I want to focus on learning-based approaches. And, what I'm presenting now is probably familiar to all of you. It is the breakthrough of deep neural networks. And the way I experienced it in computer vision, my area, people had been working on challenges like, say, object recognition in images, classification of images for decades, right? Devising features, looking into the image, computing filters, aggregating responses with SIFT, SURF, brief, other types of descriptors. But somehow in 2011, on established benchmarks, like this is the ImageNet benchmark that Fei Li put out that contains gazillions of images of objects, right? Compared to a human, the average human, the machine just made significantly more errors. Whereas an average human would make 5 mistakes in classifying a certain number of images, on the same challenge, a machine in 2011 made 26 mistakes. That's like 5 times higher error, right? And in 2011, it seemed like we can never get anywhere near human level performance. And then something almost magical happened. Then the neural networks were rediscovered and made deeper and more sophisticated by Alex Krzyzewski and collaborators. And they achieved an error on the same data set of 16.4. So quite a dramatic drop in error, right? And then, the whole community jumped on this development and developed even more refined version of deep networks, like, for example, the VGGNet, based on the VGG team that I'm currently hosted at in Oxford. And this was quite a success. And this is even not the end. This is 2016, is already a few years back. But what you see is we did manage to beat the human on a challenge which I would argue the human was designed to do, right? Obviously, humans were not made for playing chess by evolution. And so for me, it's never been a surprise that we can build a machine that can beat humans at playing chess. And as you know, this was done years ago. But for me, the real breakthrough of artificial intelligence is to beat humans on arguably a challenge that the human was designed for by evolution. One challenge, but there's more. And so in the wake of this work, we and many in the community looked into, can we deploy deep networks, not just for classification of images, but for numerous other tasks beyond object recognition. For example, in 2015, almost 10 years ago as well, we showed in the flow network, our team showed that you can actually estimate optical flow with a suitably trained deep network, which you provide 2 images, and then the network predicts the flow field at an unprecedented precision. And in fact, to my knowledge, pretty much any competitive optical flow method today goes back to that seminal flow network. But also things like, video object segmentation, where we show that you can, fine tune a given neural network on a challenge like video object segmentation so that it can really segment pixel accurate objects in very challenging videos. Or this is more recent work where we showed that even like reconstruction and localization challenges, the classical SLAM problem of simultaneously localizing the camera and mapping the 3D world, we can dramatically boost the performance of these methods by suitably trained deep networks to get a completely unprecedented precision for tracking a single moving camera. And once you have a single moving camera, you can even train deep networks to generate, as you can see, entire 3D worlds, kind of virtual copies of the 3D world obtained from a suitably trained neural network here, Felix Wimbauer and collaborators in 2021. And again, we have this capability to recover the 3D world. That raises the question, can we study the 3D world? Can we analyze 3D shapes and start comparing them, relating them? And there's a lot of work in that field. This is just a few kind of recent representative works on shape space interpolation, on modeling flow fields to model deformable shapes with occupancy flow, or on this very beautiful work of a former postdoc of ours, Emanuele Rodola, on studying latent spaces for shape representations, using shape autoencoder and seeing whether you can decouple the extrinsic shape variation and the intrinsic. So these are a lot of also learning-based approaches, as you can see, to this challenge. In this talk, I want to focus on two parts. The first part is going to focus on correspondence and matching. And that's because once you study shape similarity, one of the central notions that also I believe humans employ is the concept that there is some correspondence between shapes that puts into correspondence points on either shape. And while in this example, in most examples that were studied in shape analysis, typically people look at isometric deformations of shapes, where corresponding points have where pairs of points on either shape have the same geodesic distance. So deformations that preserve this geodesic distance are called isometric deformations. And when you articulate a human, you typically get isometric deformations. But then, humans can compare shapes that are very distinct from different classes. You see a dog, you see a camel, and you're going to say they're similar. And you will be able to say that there is some correspondence that puts in correspondence the nose or the paws or the tail, or you name it. And these shapes are very far from being isometric because there is significant stretching or shrinking involved in deforming one shape into the other. And moreover, this is very challenging. Why? Because locally, the shape parts don't look anywhere similar. The back of the dog, if you just look at it locally, doesn't look anything like the back of the camel. And the paws of the dog are very different from the paws of the camel, etc. Right? So just local similarity of shapes will not work. It will not give you a good correspondence. And so one of the challenges we faced and we addressed is how can we exploit the multi-scale notion of shape in order to compare shapes of very different, that are very non-isometrically deformed versions of each other. You have to look at shapes on multiple scales. And so my student Marvin Eisenberger and his collaborators looked at this work, looked at this problem, and there's two works that I want to present. One is a classical approach, kind of an energy minimization approach of how we used to do it in computer vision and related fields, published in CVPR 2020. And the same year, we proposed a deep learning-based formulation of this approach. The first one is called smooth shells. The second one, we call it deep shells. The key idea is that we introduce this shell operator. And what it does is it starts with a shell, like a mesh, and it computes the Laplace-Beltrami eigenfunctions, phi k. And what you can see here is it basically takes the shape and projects it onto the Laplace-Beltrami eigenfunctions. And then we have an exponential downweighting of high frequency, with a cutoff frequency large k, and basically any frequency beyond k will be exponentially suppressed. That's essentially what this weighting provides. And then you sum them up with kind of down weighting high frequency. And as a result, what you get is kind of stick figure-ish approximations of the initial shape X. Here, S6 and S50, these so-called smooth shells, that are, stick figure-ish approximations where you have the property, obviously, that if you let large k go to infinity, you get back the original shape. So we get a whole family of increasingly coarse versions of that initial shape. And so the idea is to use that, tap into that family of shapes and do a multi-scale alignment. And for this alignment, we go into an embedding. So we embed each shape, X and Y are the two shapes that we want to compute correspondence for. We align them with an embedding that uses both this extrinsic smooth shell approximation at different levels of K and the intrinsic feature correspondence that we get from the eigenfile Laplace-Beltrami spectrum. So spectral kind of components. And that is, so we embed this three-dimensional shape into a basically 3 plus K plus 3 dimension. The first, so the 1, 3 is for we also store the normal vector. And so then we do an alignment on this representation where the alignment with respect to the extrinsic representation is nothing but the vertex-wise translation tau, and that can be computed in a least squares fashion. Once we have a correspondence, we can compute a transformation tau that aligns the two extrinsically on the shell level K of X and Y. And the intrinsic alignment is done by a matrix that's often called, this is work by Max Ovsyannikov. Damn it, what's the term that he, functional map is what they call it. Sorry, I just lost it. Yes. And so both of these can be computed efficiently. And then the loss function that we set up to align the two shapes contains 3 terms. The first term is the alignment of the on the extrinsic representation, and that basically is like a Frobenius norm where P is a permutation matrix that basically makes sure that the corresponding points are aligned, and xk star is this transformed version of xk with the transformation tau. Right, that's what I showed you earlier. And then the second term is a feature similarity that basically assures that corresponding local features are similar. Then there is an as rigid as possible regularizer that says we want a transformation of the vertices that is as rigid as possible. Very popular regularizer in this field of shape analysis. And that can be minimized in this coarse to fine manner on multiple scales. And so this is what you see here, kind of animated. We try to match a dog to a horse. And as you can see, kind of in this color-coded version on the multiple scales, the blue dog is aligned with the yellow horse. And then it's a little bit hard sometimes to visualize correspondences. We'll see that in a second. But you can quantify errors because there's by now quite a number of benchmarks, the Tosca benchmark, the Scape benchmark, TopKits, Recon, etc. So there's a lot of different benchmarks, and then across all these benchmarks, this proposed smooth shells approach is quite superior to everything that was out there at the time of publication. And I think the main reason is that it really does the correspondence estimation across these multiple shapes with the shell operator. And I think that, as I mentioned, for in particular non-isometrically deformed shapes is vital to get a reasonable correspondence. What you see plotted here, I didn't mention, is always the geodesic, relative geodesic error on the x-axis and the number or the percentage of correspondences where we have achieved that error. So obviously you want to be in the top left of these plots. What's more is we have this the smooth shells. Actually, this approach creates a very smooth transformation because it's done on across multiple scales in a coarse to fine manner. We tend to get very smooth transformations. In fact, if you look closely, here is the correspondence visualized by these tessellations, right? And the less they're distorted, the better. This is a good indicator of how good the correspondence is. But you can also highlight in red the points where the correspondence is off, where you have a significant error. No, sorry, what's highlighted in red, sorry, that was wrong. What's the highlighted in red are the points where the mapping is non-smooth. And what I wanted to highlight here is that our mapping is in fact much smoother than the ground truth. which indicates that possibly the ground truth is not perfect. This is unfortunately always the case with these benchmarks, that even the ground truth is not always perfect. And in fact, what you see with the smooth shells is you get non-smoothness of the mapping only in locations where you would expect it, under the arms, in the belly, because that's where you have significant bending. In the rest, on the breast, on the arms, you would not expect any non-smoothness, and the smooth shells give you very smooth mapping. So it's a very nice feature that not only is it very accurate in terms of pairwise correspondences, but it also gives you very smooth mappings. But it doesn't always work. Here's a failure case, or some failure cases. And in fact, these are not obvious. These are somewhat difficult challenges. For example, where we try to map a fat pig to a camel, and they clearly don't look very similar, and they're very far from isometric. Or we have two persons from, I think, different data sets, with very different articulation and etc. And here what you see is that corresponding, there is a flipping of orientation, right? So on the left example, the right hand of one person is mapped to the left hand of the other person. So there's clearly a flip in orientation, which actually happens not so rarely on humans because they are nearly symmetric, right? What distinguishes the front of the human from the back is just a nose, basically. There's not so many feature differences. So it's not surprising that sometimes it's going to flip, right? And on the animals, similarly, there's a certain symmetry, and here it flipped the front legs. The left leg is matched to the right leg. So there is room for improvement. And so we also thought, how can we tap into the power of deep networks to improve here? Now let's look at this approach. Here's the loss function, right, that we're minimizing. One of the biggest challenges to make this learnable is you have to make things differentiable. It's a classical important concept in making things that are learnable. You have to be able to back propagate. You have to be able to do gradient descent to train weights of a network. And for that, your loss function, whatever you want to deploy, must be differentiable. But here, this step of mapping to the minimizer over the correspondence, this permutation matrix is a binary matrix. This is not a differentiable step because P is binary in the first place, right? So what can we do? We can relax P to a real valued matrix, pi, and then the loss function is actually nothing but the optimal transport loss, a loss function that is very popular in many areas of applied mathematics related to the Earth mover's distance here. And typically, the way you minimize this loss function with respect to this correspondence function pi, real valued now, is that you typically add, so this is the correspondence function, and x star is again the transformed version of x, and we're trying to find the correspondence between the points on either shape after aligning with this transformation tau. Right. And typically, as I said, in that community, they add the entropy as a regularizer to create a bit of smoothness. And that way you can much more easily minimize this using typically the Sinkhorn algorithm is a popular choice. And there are people like Gabriel Peri and Marco Cotturi and others who have worked a lot on this field recently. And obviously other fields, medalists, etc. So I don't want to go into optimal transport. This is a whole separate topic. But here we use it as a loss function. And in addition, what we do is we don't just minimize the optimal transport, but we actually do what's called unrolling. So we compute this correspondence using iterations of the Sinkhorn algorithm, and each iteration of that Sinkhorn that estimates the correspondence can be considered as a layer in our neural network, right? So we do several iterations of the Sinkhorn in alternation with this alignment computation that is a least squares estimation step. So that's a single step, but we can put all of that into a big neural network. And that allows us to take now this loss function and do an end-to-end learning. And since we use this loss function, the same loss function, we don't need ground truth on the correspondence. The network is trained to generate a minimal smooth shells mapping, basically. And then once you've trained it, just with a set of pairs of shapes without any ground truth correspondence, so in that sense, it's fully self-supervised. You get a network that you can then, once you've trained it, apply it to a pair of given shapes and get out correspondence. I forgot to mention in the beginning, we actually use an off-the-shelf shape descriptor here, the shot descriptor, but in our experience, it doesn't really matter what descriptor you use. We found possibly we can even go without an initial descriptor. What's important is we then apply spectral filters on the to generate learned features, and these are then used in the loss function. Yes. So this is the whole approach that we call deep shells. And why is it important? Self-supervised approaches here are very important because it's almost impossible to get good ground truth, right? As I mentioned earlier, sometimes ground truth can be erroneous. If I give you two pairs of shapes, what is the correct correspondence, right? I mean, not even a human can tell you typically between a dog and a camel, right? So there is no, hard ground truth. And we can also not ask a human to label the full shape. Sure, we can say the nose is here, the nose is there, but how about all the rest of the points? There's lots of them, right? To find a ground truth for dense correspondence is practically impossible. And so self-supervised approaches are, in my view, the right way to go here. Here's a quantitative comparison again on different data sets. And what we found is very important. This is the notorious issue with learning-based approaches. They often work well on the training set, but how about on the test set? And how about if you train on one data set and you test on a very different data set? And it's a notorious problem with deep learning approaches that they work well on the test set, provided it's from the same data set, the same distribution, the same setup, the same types of shapes with the same meshing, etc., etc. What if you look at a completely different data set that was scanned by a different person in a different lab, that was curated differently? Does it still work? And here, what we find, especially in this transfer, it still works super well, right? That if we can train on the escape data set, we can test on the Faust data set and vice versa, and etc. And we still get not the same performance. So there is a bit of a performance drop when we switch and apply it to a different data set, but it still, it does reasonably well and much better than baseline approaches, as you can see. Here's a comparison, just a qualitative comparison, not quantitative. Previous was quantitative. Now here's the qualitative comparison. And here again, note here that, a lot of the baseline methods, depending on how some of them are somewhat, I would say, engineered. And so they often generate a strange tessellation in the transformation, right? As you can see here, like a piecewise constant mapping, not a smooth mapping like the smooth shells do. But in contrast to the smooth shells, for this very difficult case, where the smooth shells gets the distortion, the orientations flipped, and the deep shells still provide you the right correspondence. And so you get an approach that is a trained network that you can apply to a pair of shapes, and it will give you quite reliable correspondences, even for very non-isometric shapes. Here, for example, we can map a horse to a dog, or we can map the same horse to a human. And if you look closely in the tessellations, you see it. You really see how the toes of the horse, the hooves, I think they're not called toes, hooves, are mapped to the toes of the human, and the nose is mapped to the nose, and the finger tips to the hooves, the front hooves. So it is a very accurate alignment. Accurate in the sense that it is very consistent with human notions of shape similarity, and possibly with evolution, right? Because you can argue that somehow all these animals, creatures evolve from similar shapes, right? And so, even, the functionalities are mapped properly. Now I come to the second part. Once you talk about shape correspondence, there is an understanding, and I mentioned it before, that you can somehow deform one shape into the other, right? And so that in itself is a separate question. Given two shapes, can we hallucinate a family of shapes that somehow interpolate between the two shapes, such that, let's say, if we parameterize it with the time t, that at time 0, the shape is consistent with the first shape, and at time 1, it's consistent with the second shape, and in between, it deforms continuously. And I think this is something that humans do, right? If you see two articulated versions of a human or an animal, you can imagine in your head how it deforms from one into the other. This is something that we've studied for many years as well. And again, there is a classical approach using divergence-free vector fields, a very beautiful mathematical framework that Eisenberger and collaborators developed. And then there is a deep learning-based approach that we called neuromorph, collaboration with a team, actually the team in Oxford that is hosting. And for time reasons, I will not go into the first work, but if you're interested, I recommend reading it. I really like it myself, and I've given other talks on that one, but here, for time reasons, let's focus on the learning-based approach because of the focus of the seminar being on learning-based methods. So here's the idea. Given two shapes, x and y, we want to create a family of intermediate shapes such that it deforms the first into the second, or into something that is as close as possible to the second shape. So basically we say, find a family x of t where x of 0 is the initial x and x of 1 it has a minimal distance to the shape y. So that's the loss that we want to penalize. And you can imagine we use very similar loss functions like we've had them before, typically, some kind of optimal transport loss. Now what we do is we want to deploy deep networks on this mesh representing the shape in order to align the two shapes and to create that family of intermediate shapes. Right? And so we conceive like a deep network architecture that consists of fairly classical and you could say standard architecture that's been developed for point clouds and can be used for meshes. It consists of edge convolutions, then max pooling, concatenation operation, and the multi-layer perceptron. So these are the different steps in this. These are, I would say, fairly established components of deep networks these days. Nothing very fancy here, right? And we use these to extract features on that mesh, n times 3 and m times 3. So we have two meshes with m and n vertices, all three-dimensional. And for each vertex, we want to extract a correspondence. And then we use a softmax operation on this n times m matrix to create a correspondence, right? And this is same as this function that we called pi earlier, the correspondence function. It basically models the permutation of the vertices to align y and x. And then we want to model a family of deformation, a family of shapes created by a vector field. And what we do is we start with the initial shape x, and then we want to add a displacement delta over time, right? And that displacement is a 3D vector at every vertex as well, right? That we call delta. And the input for training is this offset. Basically, we have pi y minus x, and that should be minimized. And what we give this approach is the initial shape x, the error, how much error is still there in the alignment of y and x, and then this parameter t. And the goal is, given that input, can you predict for that time step optimal deformation to minimize the discrepancy at that given time t? And what we can do here is we can actually use the exact same architecture, the same graph convolutional architecture and graph operations to define the interpolator. So this is nice. We don't have to cook up a new network architecture. We can use the exact same one. Why? Because the initial architecture was designed to create a feature vector at every vertex of the shape. And the interpolator is designed to create a vector at every vertex of that structure, right? At every vertex of the shape, we want to create a 3D vector. So in some sense, it's the same architecture to create not an n by m matrix, but an n by 3 matrix, a 3D vector delta for every vertex. And so since it's the same output architecture, we can also use the same network architecture to do. And then we have a big network that can be trained in an end-to-end fashion in a self-supervised manner using 3 loss functions. One is the registration loss. You know, this is much like what you've seen, this optimal transport alignment, some kind of least squares loss. Then an as rigid as possible loss, you've seen that before, except here it's for the whole family of shapes. So we say for the whole family of shapes from x0 to xt, we always want consecutive shapes to be deformed in an as rigid as possible manner. So the deformation from xk to xk plus 1, and you see here we actually symmetrize it to get the symmetric error loss here. We want that to be minimized for the whole family of shapes from 0 to t. And then we additionally add a geodesic loss to stabilize it a little bit. This is a loss that somehow favors isometric deformations. It doesn't require things to be perfectly isometric, but it says in the case of doubt, it prefers isometric deformations. Because dx and dy are the pairwise geodesic distances for pairs of points on x and on y. Pi is the permutation matrix, right? And so what we're saying is that these pairwise geodesics for the corresponding point pair should be the same, or should be as close as possible in this least squares sense. So that kind of softly favors isometry. We apply this, we can, once you interpolate shapes, it gives you a correspondence, right? So because you create a family of intermediate shapes and you can follow where does that point on shape 1 go if I deform it through this family of shapes. And once we do that, we can compute correspondence, and we find it's actually significantly more accurate, or somewhat more accurate than existing approaches, also more accurate than the deep shells. Not that much better than deep shells, but a little bit. And so there is a value also for correspondence once you start modeling the whole family of interpolating shapes. And also on the Schreck benchmark, we find it's actually quite accurate. Here, the neuromorph is more accurate. Here are some qualitative examples. I think that's always interesting also, not just to see numbers, but to see examples where you see, again, comparisons to the, for example, the smooth shells here, where the orientation is flipped. This approach does preserves the orientation, the neuromorph, as we call it. And what's nice is it can also be applied to partial shapes. This is important for scanning. For example, I said we can recover the 3D world, where very often when you scan an object from one side, well, guess what? Then you only have that side of the object. And then if you have a shape comparison approach that needs a beautiful, complete mesh, many of the shape approaches do need that, then that's not very practical, right? You need something that can also be applied to partial shapes and that gives you a reasonable correspondence, as we can see here. Like the buffalo is mapped to something, I think it's a half a bear or something. And still the correspondence for the parts that are there is fairly good. So that gives us an approach that allows us to align very different shapes, to compute correspondence across very different classes of shapes. And so the second paper, the neuromorph, also comes with a database where where we computed, very accurate correspondences across different shapes, and people can evaluate their algorithms and see how well they are able to recover shapes, or for whatever other purposes they want correspondence between very diverse sets of shapes. And we can visualize how the accuracy also in another way. We can look at one of the two shapes and say how big is the correspondence error on the different parts. And it's color coded in red, and you see that the error on neuromorph is very, very small. It's much less reddish than most baseline approaches on this example. So what is this good for? You can deform one shape into another, and that way you can create what's called digital puppeteering. You can basically take a cat and deform it into a human or something as close as possible to that human figure. Right? And this is what's seen here. Not that my cat can actually do these things, right? But who cares, right? In principle, this allows you to deform things, and so you can do this kind of, it's called digital puppeteering. You have a human, articulating in some fashion or dancing around, and then you can take a different shape and basically frame by frame align them to the human, and as a result, you create, you can basically animate the gorilla or here the dog to do the exact same movements that the human. I guess this, approaches could be very useful for Hollywood. If you want to animate a digital character, there's very little you have to do. You have a baseline human articulating, and then that allows you to animate the character in a fully unsupervised manner here. In Hollywood, in my experience, from what I know, they often use a lot of manual tweaking. Here, there is no tweaking. This is just straightforward application. So to summarize, I talked about 3D shape analysis, about different challenges in shape analysis, about correspondence estimation, about matching of 3D shapes, about interpolating two given shapes. And I showed that we can deploy the power of deep neural networks with suitably trained self-supervised deep networks to really give fairly compelling results on even very diverse classes of shapes. That's all, and I thank you for your attention.
Okay, thank you very much, Daniel. That's a very nice talk. Right, I'm just going to pause the recording and then I'll invite questions.